All right, let's talk simulations. So simulations specifically in probability. Most of us know the game Rock, Paper, Scissors. It's a great game. You could play that game with a friend, or you could simulate playing the game instead of actually playing it. You could use dice, spinners, tables, etc. to pretend you're playing the game and figure out the outcomes. So what are probability simulations and why do we use them? Well, a simulation provides a way to generate outcomes that can be used to calculate experimental probabilities. Suppose that Edam's Cereal Company offers 1 of 5 surprises in each box of Yum Yum cereal, and we wanted to determine the probability of getting all 5 surprises in just the first 10 boxes that we purchase. We could actually purchase the cereal and record what type of surprise is in each box, and to do this for one or more sets of 10 boxes. The problem, however, is that this could become costly and use more time than we have available. Other situations actually may be dangerous for us to carry out, such as situations involving driving cars at high speeds or working with explosive materials. In these situations, we may choose to simulate the actual event and use the results of the simulation to determine experimental probabilities. So let's look at an example. If a baseball player gets a hit 3 times out of every 10 at-bats, how would you run a simulation for this baseball player using that probability for the next 6 at-bats? So you have to think of, his probability is 3 out of 10. 3 times out of 10, he gets hits. So think about how you could simulate that. Do you have an idea? Give it a couple minutes and think about it, and then move on, and I'll explain one possible solution. Okay, you could use a random number table and use the digits 0, 1, and 2 to represent a hit, since that would be 3 hits, and the other numbers 3, 4, 5, 6, 7, 8, 9 to represent no hit. So I used a random number generator, and I just generated some digits. And they were in groups of 3, so I looked across a row to say, okay, those are the next 6 at-bats. Using my setup for my simulation of the numbers 0, 1, and 2 are a hit, I looked across that first line of 370, 309, and I said, oh, there's a 0 and there's a 0. Those are both hits. So there's 2 hits. And then how many not hits are there? Well, there's a 3, a 7, a 3, and a 9. So there were 4 not hits. So on the next 6 at-bats in that simulation, he would have 2 hits and 4 not hits, because that's a total of 6 at-bats. You could look at the other rows and determine whether or not how many hits he got and how many hits he didn't get. It's not going to be exactly the 3 out of 10, because remember Bernoulli's law of large numbers. We would have to repeat this experiment a lot of times in order to approximate that empirical probability of 3 times out of every 10 at-bats. But we have set it up to where 3 of the digits represent a hit and 7 of the digits represent no hit, so we are using the probability of 3 out of 10. Let's look at a classic example. You probably have not heard of Monty Hall, but Monty Hall was the host of a TV game show called Let's Make a Deal. Yes, there is another Let's Make a Deal with Wayne Brady, but that's not the one we're talking about. The original, this is why it was called the Monty Hall problem. Here was the game. So you're given the opportunity to choose 1 out of 3 closed doors. Behind one of the doors is a prize, and it was usually a big prize. Behind the other 2 doors hides goats, or a bad prize, or nothing at all. You select a door. Then the host, Monty Hall, opens one of the other doors, showing you that it does not contain a prize. He then asks you if you would like to stay with your original selection or switch to the other unopened door. So here's the problem. Should you switch doors? Does it matter if you switch? Why or why not? So remember, here's the 3 doors. So you choose one door. Behind the door, there is a really nice prize behind one door, and there's bad prizes behind the other 2 doors. So you pick a door. Let's say you pick door number 1. The host, who knows what's behind each door, then shows you what's behind door number 3, which is a bad prize. Then the host says to you, do you want to pick door number 2? Is it to your advantage to switch your choice from door number 1 to door number 2? This is the question I want you to think about. Could you do a simulation? How would you record your results? Do you want to make a tree diagram? Take some time and formulate your answer. Does it matter if you stick or switch? Make sure you have mathematical justification for your choice. Don't look up the answer. Really try to practice your thinking. I'm going to end this video here. This will be part 1 of the video. Part 2 will show you the solution. So make sure you formulate your answer before you look.